to be at Fields. It's a great pleasure to be lecturing again at a chalkboard. So the work I'm talking about today is joint with Jim Freitag, Ramey Jaoui, and Ronnie Naglu. We'll always be working in K, some saturated differentially closed field. And C will be the constant field. So the starting point for this is an old result of Poizat from the mid-70s, I think. It's in one of the Paris seminar volumes. I don't think it was ever published in a journal. Look at the solutions to the equation x prime equals xx double prime. So this is an order 2 differential equation. What he proved is that the only order 1 differential subvariety is the constant field. It's just given by x prime equals 0. Of course, if x prime equals 0, that'll be a solution to this, but it's the only one. Now, this is at least the first example that model theorists had that differential algebra is weird, that it's very, very different from the differential algebraic geometry is going to be very different from algebraic geometry. So this is a transcendence degree 2 set. I mean, x and x prime are going to be algebraically independent elements for a generic point. But and in algebraic geometry, you think if you have something of transcendence degree 2, it'll have a lot of transcendence degree 1 subvarieties. This says that in differential algebra, that may not happen. So this is an example of something which is, it's the first example of something that's, okay, sorry. So, and I'm going to rewrite these equations most of the time and to sort of throw out the x prime equals 0 locus. So I'm going to think of this as being x double prime over x prime is 1 over x. And this is going to be the first example of an order greater than 1 strongly minimal set. It's also an example of something that's irreducible, but has Morley degree 2. So there are 2 rank 1 types, the type of x prime equals 0 and the type of a generic. Pardon? This set's strongly minimal. Sorry, so this is the first example of an order greater than 1 strongly minimal set. The original variety is something that's irreducible, but Morley degree 2. Again, very different from what one might expect, and just using algebraic geometric intuition. There's a proof of this in my lecture notes on differential fields. Probably none of you have read the proof because it's 3 pages of algebra, sort of doing calculations in the differential polynomial ring, and eventually showing that if I take any order 1 polynomial, the differential polynomial that divides this one, then x prime has to divide that. I'm not sure anyone has read that except Jim Freitag. In his thesis, I think an unpublished part of his thesis, he gives a variant of this. You look instead at x double prime, x triple prime, and now x double prime equals 0 is the only infinite proper subvariety. And then I had suggested he look at this problem because this is something, again, that's quite weird. It's a, it's a Colchin closed set, and all the Morley rank is constant. It's rank 2, but all the Morley rank is concentrated in the subvariety. So the generic type in the sense of the Colchin topology isn't generic in model theoretically. And again, this is an even worse computation. So let me just give you some examples of.
So Dave, sorry,
Yeah.
Dave, this example is also strongly minimal outside the infinite, outside that.
Yeah.
Yeah.
Yeah. Again, this is the only way you can get a differential algebraic subvariety of this is to take x double prime equals 0. So by quantifier elimination, there's nothing else. So again, some other examples of higher order strongly minimal sets. And so there's this, as I said, you start with the example of Poizat. It was generalized in work of Brzostowski. I'm not going to state exactly what his result is, but he sort of finds a class of different strongly minimal sets, but where Poizat's computations and proofs more or less work as is. A more natural example was done by Colchin, which is sort of the first Pan-Lavey equation. X double prime is 6x squared plus t. And sort of in a letter from Colchin to Carol Wood, he gives a proof that this is an example of an order 2 differential subvariety that has no order 1 subvarieties. The next examples really come in Hrushevsky-Sokolovich. And this is when you get to Monon kernels. So just to remind you, here A is a simple abelian variety. So no proper infinite sub-abelian varieties. Not isomorphic to a variety defined over the constants. And O sharp is the minimal infinite definable subgroup. We can give a more concrete characterization as the Colchin closure of the torsion points. Naglu and Pillay looked at Pan-Lavey equations. With generic parameters. And showed that these were strongly minimal. Showed that these were strongly minimal and trivial. I'll say a bit about that in a minute. Freytag and Scanlon looked at the equation satisfied by the J function. And showed these were strongly minimal, trivial. I guess these are order 2 equations. These end up being, the order ends up being twice the dimension of the abelian variety in these cases. Let's see. what's interesting about these things is all of these results are kind of hard. I mean, the Poizat example and the Colchin example involve sort of horrible calculations. I mean, the first version of my differential fields node had the Colchin example in it. It later appeared in his collected work, so I took it out because I didn't want to claim that the argument I gave was completely right.
Dave, Colchin is Painlevé 1, right?
Yeah, Painlevé 1.
Yeah.
Yeah. Of course, this is a non-trivial argument. This, depends on some of the a lot of the work done by the Japanese school in differential algebra. This result uses Pilar's stuff on excellent Weierstrass theorem for J functions. So I find this an interesting point that it's very hard to show. For the most part, it's been very hard to show anything is strongly minimal, but maybe almost everything is. So some recent results, one of Remy, you take a generic planar vector field, a polynomial vector field over the constants. Sorry, I think I want to say of degree greater than or equal to 3, but maybe I want to say greater than 3. This is going to be strongly minimal. And a more recent result of Matthew Devilbus and Jim Freitag. I want to look at f of x equals 0, where let's say it has order n, degree at least 2 times n plus 2, and differential transcendental coefficients. This is somehow saying that a reasonably complicated differential polynomial, if it's generic, it's going to be strongly minimal. So even though it's very hard to show particular examples, this somehow says most of them are. Okay. Let me just remind you of the trichotomy in this case. And this again goes back to Hrushevsky and Sokolovich. So there was a model theory year here in, I think, 96, 97, and Anand gave a course where he did some of these things. So again, I have x strongly minimal. Then one of 3 things happens. And basically you get the Zilbert dichotomy, but in a quite strong way. The Zilbert trichotomy in a quite strong way. Either you're non-orthogonal to the constants, or you're non-orthogonal to a mononkernel. Or you're trivial. So the non-locally modular cases, the only non-locally modular case is the constants. The only non-trivial locally modular cases are the mononkernels. As a result, which I think is, well, it's probably folklore. That's a corollary to this. Suppose I have an equation f that's over the constants, an order bigger than 1. If it's strongly minimal, it has to be trivial. But part of this is easy, that if the order is greater than 1, it can't be non-orthogonal of the constants because the transcendence degrees are wrong. It takes a slight bit of work to show that if it's that because it's defined over the constants, if it's locally modular non-trivial, it can't be non-orthogonal to a Manin kernel. Okay, so this says that the Poizat example, at least is an example that's trivial, which okay, so that's the introduction. Pardon? And the Jolly ones are, yeah. And the other ones, you have to give some kind of proof that they're trivial. And one of my favorites is I find the Pillay-Noglu proof of triviality I find particularly amusing because it uses an essential way that there are non-generic things that are not strongly minimal in the proof that the generic things are trivial. Okay, so here's the theorem what I want to look at today is I want to consider the general family of equations which Poizat's equation fits in. Let f be some rational function of the constants, and I want to look at x double prime over x prime equals f of x. Okay, so the first observation and this, I think, is actually in Poizat's original article. Suppose you take g of x. So if g is in C of x, and g prime, which I'll use to denote just the usual derivative of g with respect to x, is f. So this says I have a rational function f, and I can integrate it as a rational function. Then if I look at the differential equation g prime equals g of y plus c, and I differentiate this, I see that y double prime is f of y prime. Okay. So if I have a function f that can be integrated, I'm always going to have an infinite family of one-dimensional subvarieties, or a function from this variety to the constants. Okay. So this case, I get something of rank 2, and I get something that's non-orthogonal to the constants. If I have time, I'll say a bit more about what some things that could possibly happen in this case at the end. And our theorem is somehow that the converse holds, that if f has no antiderivative, in C of x. Then the equation defined is strongly minimal and by necessity trivial. The interesting thing is that, pardon, thank you. That unlike the Poizat example, this has a, well, unlike Poizat's proof, this is a very short and memorable proof that I'll shortly give. So first, how do I use no antiderivative? Well, now there's an advantage to having spent years teaching freshman calculus. So I have a rational function. I can do the partial fraction decomposition. And since I'm doing it over an algebraically closed field, I can always write f as a derivative plus a second term a derivative plus a linear combination of terms 1 over x minus alpha I. And so f is, now of course, things like this don't have, to integrate them, I would need to introduce logs. So being integrable is exactly saying, being non-integrable is exactly saying some Ci is not 0. Equivalently, I can take f of x and write it as a Laurent series. Yeah, the sum from some r possibly negative to infinity ai. Let's see, sorry. Let me say without loss of generality. I want to have a simple pole at 0. Okay. I could, because the alpha i's are constant, if I do a change of variables x minus alpha I, that will just change the problem to one where I have a pole at 0. And now if I write out the rational function, what this ends up telling me is that a minus 1 is not 0. So there's a residue. This is a residue. Okay. Okay, so that's what I know about x. So let's suppose not. What would that say is that, well, I would say that over some field k delta, not necessarily over the constants, maybe I have to add some terms in. There's a solution y that's transcendental over k. But y prime is algebraic over ky. Okay. This is saying that y and y prime satisfy some equation, algebraic equation over k. This gives me a first order equation. So we're going to work in the Poizat series. So I take the union of the Laurent series and y to the 1 over n for all of it. And I mean, the fundamental theorem is this is an algebraically closed field. So I can identify y prime with some u in the Poizat series. And I want to define a derivation delta that if I differentiate a series, I'm going to get what I usually get. First, a series where I differentiate the coefficients, but then I get u times the sum of the ai minus 1. So we've chosen this derivation, putting this u in.
Sorry,
So
Dave,
this-
can I ask something?
Sure.
Yeah, so on the first line, I mean, you're identifying y prime just as a field object. I mean, just because it's algebraic over algebraic over y, right?
Right. Right.
There's no derivation yet.
There's no derivation yet.
Okay, just to
But now
clarify.
I built the derivation, and I've done this exactly so that delta y is u. Okay, so I've chosen u so it satisfies the right algebraic equations with right algebraic equation with except to y. And now I've defined the derivation so that delta of y is u. So this extends the derivation on k of y prime.
And it's on the full Poizat series?
But the derivation is now on the full Poizat series, but it extends the natural derivation we'd have on delta y prime. Okay. Okay, so sorry, let's write u out as a series. Let's say it's the sum from 0 to infinity and y to the r plus I. What? Well, because I'm putting the r, I'm putting the r here. So it looks something, one way to write it is something like this. So y double prime is u prime. Pardon? I equals 0 to infinity ai y to the r plus I over some n, just as in some Poizat series. Sorry, I changed things a number of times as I was writing it down. So when I write out the derivation, first I differentiate the coefficients. Then I get u times the usual derivation. And let's just notice, let's see this part, if I look at the valuation, which is the lowest term with a non-zero coefficient, This is at least R. So now let's look at y double prime over y prime, which is u prime over u. And let me just write alpha here for this part divided by u. And so I'm dividing by something that has value r. So this has value greater than or equal to 0. I'm going to end up ignoring that. Here I just cross out the u. Okay. And this is supposed to be equal to f of y. Okay. All the terms here have powers that have powers of y that are non-negative. Here, if you look at the y to the -1 coefficient, like that happens when r plus in is 0, and now I've multiplied that out. I've multiplied by 0. So the y to the -1 coefficient is 0. So this can't be equal to f of y. So you see what I mean when I say this is sort of a memorable proof. It's not so special, this equation. I'm gonna,
Dave, can you say again why the coefficient is 0, the last coefficient?
Sorry, yeah. If I look at the coefficient of y to the -1, where does that come from? That comes from when r plus in is 0. I multiply, so I've multiplied by 0 that term.
Oh, right, okay.
Yeah, so it's just why you take any power series, you differentiate it using the standard derivation. You don't get a -1. You don't get a -1 term. Sorry, there was another question.
Yeah, I was asking about extending the derivation.
So I mean, you have to check that this is the usual derivation I'd put on the Poizat series. I would define the derivation so that y has derivative 0 or derivative 1. And so I would just not have the u term here. That's the standard derivation. But just, you can check this is a derivation and it does what I want it. Let me give a strange corollary that we've just discovered in the last couple of weeks. Let's say, again, assume f has no antiderivative. Now I want to look at this equation, y double prime plus f of y prime. Plus, and now I'm just going to write down a generic rational function with sum from 1 to n, or 0 to n, of cix to the I. Sum from 0 to m, dix to the I, where the ci di are algebraically independent constants. Let's see, and x's or y's. So I've written down some kind of generic rational function here. What I can conclude is that this has to be orthogonal to the constants. What I don't know is, sorry, let's make an equation. What we don't know is whether it has to be strongly minimal. but it's going to be orthogonal to the constants. And this follows from a specialization theorem of Jaulet, that under you have a nice map between D varieties where everything's defined over the constants. If when I look at the D points, if a generic fiber is non-orthogonal to the constants, then all the fibers are non-orthogonal to the constants. Since we know there's some fiber, if we chose all the CIs to be 0 and all the DIs to be 1, I'd get a 0 here, and I know that's orthogonal to the constants, then the generic fiber is going to be as well. These are examples of something called Lennard equations. So these are equations of this form, which arise in things like circuits, I believe, and maybe some kind of planetary motion things. They're studied a bit by applied mathematicians, and they try to prove things like whether you can find solutions in Liouville extensions. Now, I don't think they've ever looked at that. They've tended to only deal with special cases, mostly with F and G or polynomials. But what this kind of result says is that because things are orthogonal to the constants, you're not going to get them two-step analyzable by constants, which they would be if you could find solutions in a Liouville extension. This says something about solutions to this type of equations that we're still working on what this might mean. Okay. I want to look a bit more at these equations and try and understand the algebraic relations between them. So to give a sort of more fine structure. So I want to look, let's say, so by VF, I mean the places where x double prime or x prime is f of x. And let's let x be in VF, y be in VG, where these are generic solutions. Now I'd like to understand when can we have differential algebraic relations between x and y. Again, by triviality, I know that if I have relations, they sort of only hold. I don't need to have a lot of things from VG to get out x algebraic. It'll be algebraic over. It'll be algebraic only over 1. The first theorem, which I won't say anything about the proof of this, so suppose again for some k, x and y transcendental over k. So suppose I have two solutions like this: x is solution for f, y is solution for g, possibly f equals g, I'm allowing here. And over some field, they're interalgebraic in the differential sense. Then actually they're algebraic first over the constants. Again, that's mostly a consequence of triviality. But the derivatives don't matter. If this happens, then it's actually because x and y are interalgebraic. And the proof of this, well, it certainly makes essential use of triviality, but also the connection between transcendence and Kähler differentials. And it builds on work of Rostovsky, but also Rosenlicht, in his proof of non-minimality of differential closures, and ultimate originating really in Axe in his work on Shanuel's conjecture for powers.
Sorry, Dave, the assumption, what's the assumption on X and Y?
So it's this one, that these are, let's say, X is a solution of the equation with F, Y is a solution with the equation with G. Each of F and Y are transcendental over K.
And something about no antiderivatives.
Oh yeah, sorry, I'm in the case where I'm assuming this is strongly minimal. No. I mean, that was only in this weird, these are just F and G. Sorry, I should write this out carefully. F and G rational functions over the constants with no antiderivative.
Okay, thank you.
So we do a quick calculation. So there's going to be some algebraic function phi where y is phi of x. So y prime is phi prime of x, x prime. For this, I just mean the formal derivative of phi x prime. Take the second derivative. I get phi prime of x, x prime squared, plus, no, I get phi double prime of x, x prime squared, plus phi prime of x, x double prime. But this is y prime g of y. Pardon? This line? Yeah. So I'm just, so by phi prime, I mean just the formal derivative, but just the chain rule. I have a function applied to x. To differentiate that, I differentiate the function, then differentiate what's inside. Okay. Now I replace this by x prime f of x. I recognize that y prime g of y is phi prime of x, x prime g of phi of x. Now, rearranging terms and canceling an x prime, I get this equation. Phi double prime of x times x prime is phi prime of x, g of x, g of phi of x. minus f of x. Okay. So starting from this assumption, I get to this equation. Over the constants, yeah. Now, if this were non-zero, I would have a first order equation satisfied by x and x prime. Remember, phi prime of x and phi double prime of x are just algebraic functions over the constants. So this would give me an algebraic relation between x and x prime. And that violates strong minimality. So that tells me that this algebraic function is particularly simple. It's just a linear function, ax plus b. Now, phi prime can't be zero. That would, if phi prime were zero, that would say phi is just a constant function. It's supposed to map. It's supposed to map into something transcendental. So this is non-zero. So if the left-hand side is zero, the right-hand side has to be zero, and it has to be zero because this is true. So this also applies that g of phi of x is f of x. Okay. Pardon?
Symmetrically, the sine of x is equal to sine of y.
Yeah. Okay, so if I think of the affine group, and I think of the action think of phi as acting by composition. What this says is that Vf and Vg are non-orthogonal if and only if they're in the same orbit. So this, I mean, certainly if G was given by F composed with phi, that would give me a function from Vf to Vg, but this says this is the only way it can happen. But what about when F equals G? The same situation, but now I've got x and y both in phi of f. This would say that phi stabilizes f. So this usually doesn't happen. This is impossible if, say, f is reasonably generic, or in something like the original Poizat case, f of x is 1 over x. So in these cases, it tells you that that the algebraic closure is disintegrated. The only element of VF that's algebraic over X will be X itself. But for any other element, it won't be true. Finish up very close to the end. Pardon? A rational function. Yeah. Let me give you two examples where this does happen, and you do get algebraic closure. If f is 1 over x minus a minus 1 over x minus b, you have this function phi, which it's an order 2 function that maps f to itself. So in this case, you get at least a point that has another point in the algebraic closure. Another example. Let's let C be a primitive nth root of unity. Then, and look at the sum of the 1 over xi to the x minus 1, and phi of x is just c times x. Okay. That will permute, that'll permute this function. Let A be the places where we have a non-zero residue. There's at least one. If n equals 1, it's a simple computation shows this is impossible. So we're in the disintegrated case again. If n is greater than 1, well, I'm going to use the fact that the affine group as it acts on the line is sharply too transitive. It's going to have to any rational function that permutes any rational function that preserves f is going to have to permute the alpha i's. So there are n choices for where to send alpha 1. N minus 1 choices for where to send alpha 2. And then once I've done that, I'll know the whole permutation. So they're going to be at most n times n minus 1 affine functions that permute these things. So this tells me that I've got a bound on the size of the algebraic closures of a point. So that even if I don't know that it's disintegrated, I still know that I have Aleph 0 categoricity. And in fact, a much more complicated argument shows that n is actually good enough. That this example with the roots of unity is sort of the worst, the case where you get the most algebraic closure. Okay, so I'm out of time, so I'll stop here. I'll say we do know a little bit about what happens what can happen in the case where f is integrable. And it's sort of like everything that might happen does, but I'll stop here.
Thank you very much for the talk. Are there any questions? In the chat, maybe? Let's thank the speaker again. Thank you.
Well, I mean, so I have something that's